Morning, all the participants and the listeners in this third part of the tutorial that is focusing on the learning the target class samples and the features. Initially, I want to discuss that why this is important because in last part of this tutorial we have seen that what actually the target class learning is and why this one class classification techniques are very important in case we want to detect anomaly in given space. Okay, so let us start with that how we can go for the target class uh, learning in terms of samples and the features, considering the fact that only and only the target class samples are available during the training. Okay? And the second class samples or the other class samples are either poorly sampled, ill-defined, or either totally absent. Okay, so if we look to, if we want to discuss this target class learning, so surely the nature of the data, okay, plays a big role. And surely if you want to learn something using some machine learning model, then the amount and the quality of data also play a vital role, in learning. So in this image, we can see that there's some sort of distributed environment where there are several sources, source 1 to source n, and may be possible that the data may be coming in batch, okay, or it is coming temporarily, okay, and the master node is all in one responsible to respond all these nodes and to compute the desired outcome. So in such a scenario, if you want to concentrate on how we should learn the target class, then definitely the volume of the data is going to play a vital role. Okay? So if we say that we are going to deal with big data, so big data in terms of number of samples also, number of features also, so it could be anything. So if we are looking to deal with target class learning of big volume data, then the second thing is that how to handle this big data if the samples are arriving temporarily. You want to deal with big volume data if the samples are distributed across the distributed disparate sources. Surely, we must focus towards the train. If we want to learn something using some machine learning model, so we must focus towards the way how to extract the best samples that will be representing the target class in the best way. So that phenomena is known as sample reduction. The second thing is that we all know that not all the features are of equal importance. At the same time, the huge dimensionality, apart from the number of samples, may occur some dimensionality, okay, that may degrade the performance of any machine learning model. That could be another way. So majorly, once we see the nature of the data, especially in distributed and temporal environment, then we must think on the data reduction. Even if we are not working on distributed environment and we are working with batch data, then we should also focus on an extraction of the most promising training samples along the most promising features that will be representing the target class in best way, so that in later stage while testing, the anomaly can be detected easily. Apart from that, if you go for the supervised learning mode, especially when we have only target class samples while training, then the best way that we must explore the possibility of most promising one class classification approach. In last part of the tutorial, we have seen that there are two benchmark one class support vector classifier. The first one is the SVDD and the second one is one class support vector machine. And in past 2 decades, several modifications have been proposed over those two benchmark classifiers. Apart from that, we can also think for some other classification strategy to deal with this anomaly. If we talk about the nature of the data, then surely the nature says that data may be batched, the data may be temporal in nature, the data may be distributed across the globe, among among slaves, different slaves. Okay. Note that the temporal nature may be further categorized in two different ways. Either the samples arriving temporarily, or either the features will be arriving temporarily. If the features will be arriving temporarily, then we can conclude that we are going to basically divide the data vertically. And if the samples are coming temporarily, we can say the data is going to be, distributed horizontally. It doesn't matter whether we are looking for any statistical model or any machine learning model, then we should focus towards the data reduction techniques so that we can learn the turret class in more efficient way. Okay, so if we talk about the data reduction techniques, so data reduction technique may be, in terms of the most selection of most promising samples responsible to represent the target class in a better way. The second one is we may reduce the feature also of the target class so that those reduced features will be explaining the target class in a better way. So if you want to reduce the features, then we must go for two options, that is feature selection and the feature transformation. So feature selection is a technique where we must, choose the most promising features among the available feature space. Okay. And the feature transformation is going to plot and project the original samples to some other latent space so that the target class samples will become more closer so that the drawn of the boundary will become easier. So that in later stage, if any incoming sample must be tested, that can be easily identified that whether it is an anomaly or it belongs to the target class itself. Okay, coming to the target class guided data reduction techniques. So we may have two things. The first one is the sample reduction, the second one is dimensionality reduction. If you talk about the sample reduction or the dimensional reduction, and we are focusing towards the target class, then we must ensure that the process of selection of the training samples and the process of selection or extraction of the features of the target class must be guided by the target class itself. So if you go for the target class guided sample reduction, then the training sample must be reduced under the guidance of only knowledge target class samples, because we already assume that we do not have any other class samples as training sample. At the time of training, we have only the target class samples as training samples. So surely we must opt some mechanism or some learning strategies so that we can extract the most promising samples of the target class from the huge sample space so that they can describe the target class in better way. Okay, because the second thing is that if some other class samples are present in the training sample, then surely they may misguide the machine learning algorithms for trying the decision boundary estimation, to estimate the decision boundary. Okay. Likewise, if you go for the target class guided dimensional reduction, we may have two options. We may select the features guided by the target class, and we can transform or project the original samples to some other domain, some other space, lower dimensional space, guided by the target class only. So TR or dimensional reduction techniques must be applied considering only the target class samples, because The other class samples surely will be misguiding the objective. And we have already considered that the time of training only we have, you know, the samples of class of interest only. So the process of data reduction must be guided by the third class samples because we do not have any other option. Coming to the conventional feature selection and feature transformation techniques, those are basically correspondence of, we can say the dimensional reduction techniques to overcome from the phenomena of curse of dimensionality. So once we'll go for the feature selection, we have three options. The first one is the filter method. The second is the wrapper method, and the third one is the embedded method. In each feature method, in filter methods, we do not have any guidance actually. We do not bother about the learning mechanism. We just do some statistical analysis. So we'll go for the correlation, either the Pearson or some other correlation coefficients or LDL, and chi-square. Okay. The second one is the wrapper method. So the wrapper method says that it must be guided by the outcome of the any learning model. If we are opting any features, we must starting from the first feature to uh, t-dimension feature, and we must select the features one by one or cumulative or any random order, and we should check which feature set is giving more promising results. Okay, likewise, we can start with the whole d-dimensional features for evaluation of learning model, and we can say that up to this limit or this number of features are most promising. It will go for the backward elimination. Okay. Somehow, there are options that we may go for the embedded techniques where we follow both the benefits of filter and wrapper methods. Okay. Apart from that, we have, you can say in embedded methods, we have laser reach methods, So these are basically most conventional techniques of feature selection methods. Okay, coming to the feature transformation techniques, the techniques that are shown here, these are not necessarily belong to the target class learning. They are basically categorized in terms of batch and online. And later part, you can see that some of linear in nature, some of non-linear in nature. So a lot of techniques and a huge number of techniques of dimensionality reduction, especially for feature transformation, have been proposed so far. Okay, if you see the categorization here, types of the linear feature transformation techniques here, we can see that there is PCA, there is, MSD, there are LDA, there is, MAF, and many more. So these are types of linear feature transformation techniques. And same likewise, the isomap, LLE, and Laplacian diagram map are basically responsible to reduce the features if the data points are residing on some manifold. Because at that time, this linear transformation techniques may get filled. Like suppose we consider the example of PCA. PCA is not at all, or principal component analysis is not at all able to cope up with the nonlinearity nature. So at that time, we have some variants of PCAs are also available. That is nonlinear PC or kernel PCA. So likewise, many techniques are available for nonlinear dimensionality reduction. Apart from that, to go for the online, so online means that we should deal with distributed environment where the samples are arriving temporarily, so that we should learn the components very efficiently if the samples or batches of samples are arriving not temporarily in stream. Okay. So at that time, that can also be categorized in two types, linear and nonlinear. There are many techniques available. So it is not possible to include all those, but most important techniques have been included in this particular slide. Okay. And it is also one more thing is that it is not necessary that all these techniques have been explored for target class learning. Okay. So most of the techniques that we are watching on the screen are basically unsupervised in nature, so they are not bothering about the target class itself. But it is possible that we may extend these works towards the target class learning features. Coming to the first phenomena of target class, the guided sample reduction, there we are focusing towards the reduction of training samples so that we may get optimized performance, less computation cost. So if you talk about the target class guided sample reduction, so surely as literature says that it has not been explored too much yet. Very, very few works has been reported till date in terms of target class guided sample reduction. The first research has been reported in 2011 by Lee, okay? And the algorithm was known as extreme point selection. As we have seen that the objective of target class learning to identify anomaly, the incoming sample as anomaly or belongs to the target class. Based on, it should be based on, means it was basically looking to draw one boundary over the target class samples, such that the incoming sample, if falls apart from the, you can say, the boundary, then we can say that it is going to be an anomaly. Otherwise, surely it belongs to the, you can say, the target class. So in this piece of research, what has been done? It has been observed, suppose we draw one tangent, a normal vector to one tangent plane to, okay, to the nearest maximum number of neighbors, as in this diagram, you can see here. So most of the neighbors are making angles less than 90. Okay? And to become a point, to be a potential extreme point, okay, so before dealing with extreme point, I want to say that the extreme points are the most promising support vectors for, any one class support vector classifier. So if we know that which points are basically most promising extreme points or most promising boundary point or most promising support vectors, then if you're able to identify those points, then those points are sufficient enough to train the model, because all other target class samples must be ignored because they do not contribute too much information, because they're going to be inside the whole distribution of the data. So for a potential extreme point xi having k neighbors, so we can compute the relative vector Vij. Suppose we are concentrating on k neighbors, so these are k neighbors, so we are just trying to draw Vij. So each Vij is normalized to some normal vector Ni. Ni is the normal vector to this tangent plane. This point is supposed to be somewhere in the distribution. And if it is at the boundary point, then definitely this property surely be whole. And the number of neighbors with theta I greater than 0, surely if we compute the angle between any norm Vij and an I, so surely it will be making some angle greater than 0 of k nearest neighbors. So this phenomena is able to help us out to find out the extreme point. Okay. So to estimate the normal vector to the tangent plane, each Vij is normalized to Vij hue. Okay. And in this particular figure, you can see here, if angle between normal vector Ni and tangent J of data point vector Vij is computed, so it should be in between 0 to pi by 2 or 90 degrees. So you must bother about all the k neighbors. So for data point xi on concave surface, let us assume. So if all its k neighbors are on one side of the tangent plane, that means surely this point is supposed to become an extreme point or the boundary point of the distribution. If the data point is on the concave surface, most of the points are on one side of the tangent plane, surely, and few are maybe on the other side of the distribution, because we may also include some penalty there. Okay. So this is all about this. So if this Li is going to be 1 or nearby 1, then we may conclude that yes, xi may become the extreme boundary point or the support vector. So likewise, in distribution of n data points, we try to impose this algorithm, whether it is an extreme point or not. So we were surely able to get those extreme points. And once we achieve those extreme points, we can train our one-class classifiers, one-class operator classifiers using those extreme points. And those extreme points are sufficient enough to train the model. Okay, in this way, we can reduce the computation cost while training. Coming to the second strategy that have been proposed to select the most promising samples concerning to the target class, because it must be guided by the target class itself. So the heuristic sample reduction method was proposed by Samitier. So what it does, basically, the first identifies the cluster centers of the training set by k-means. And then all samples are sorted in descending order according to distance to the corresponding cluster center. Moreover, the farther sample is moved from the sorted set into the reduced training set. And then the training sample which have a sorted distance to the farther sample are deleted from the training set. And this process iterates now until the sorted training set is empty. So in this way, you may get less number of training samples compared to the original sample space, and hence able to reduce the computation cost guided by the target class itself. This is the third well-known technique proposed by Zhu here, and basically it uses the same concept of neighbors distribution. Let us say that the sample x0 is the data set T, and there are k neighbors of x0, and let us say that xk is defined as mean of all k neighbors of x0. The neighborhood sphere is, we can see in this diagram, the neighborhood sphere can be divided into two parts, T1 and T2, with a divisor in the hyperplane AB passing through x0. Let us say that x0. We have concluded k neighbors of for this x0. We know the x mean, okay, of this k neighbors of x0. So where the divisor is the hyperplane AB passing through x0 and perpendicular to x0 minus xk. So you must have such situation where this property must be held. So T1 is the hemisphere, that half of the hemisphere, where xk bar, that is mean, is located, and other is defined as T2. So you can see this diagram. D1 is having xk bar, and D2 is having does not have the mean. If there are more neighbors in D1 than D2, then it is generally located near the boundary point. So we can easily say that if D1 is having more number of neighbors compared to D2, then this x0 is going to be a boundary point. So to compute all this thing, Simple neighbor angle has been calculated in this proper approach where the point and the mean values have been used considering all the neighbors. And finally, when the number of neighbors in D1 is far more than D2, then the computation of this angle must be close to 1. And we can conclude that it should be a boundary point. Coming to the most recent approach, that is known as the farthest boundary point estimation approach. So the diagram that is represented here is a two-dimensional view. So the again, the concept is same. All the statistical, basically the angle and the distance from the mean of the distribution have been considered in this approach. And you see this diagram. So all this, basically the target class samples. The objective is to eliminate the less important target class samples and choose the extreme point or the farthest boundary points. It doesn't matter we are working with SVDD and what class support vector machine, this phenomena will be working. So the idea is very simple. If you see this two-dimensional view, we must go through rotation to angle by angle, where delta theta is some constant angular moment, and for each angular direction, we must compute the farthest point. In same way, we may get the more flexible boundary. So that is how we can reduce training cost to some extent. And surely this method is most promising compared to the remaining one that I've seen so far, because it is considering the farthest boundary to each direction. Okay. So why I'm saying that this is the most promising, because once you see this approach, the basically recursive algorithm is not at all needed. Means once you go through all the directions, and in all the direction you are able to identify the extreme points. Those extreme points can be treated as the most promising boundary points, and you'll be getting the most flexible boundary. But in case of the extreme point selection algorithm, very often some other mechanism where we were looking for observation of each and every point, whether it belongs to, whether it is an extreme point or not. So surely it is not basically deterministic that after how many iterations we'll be getting the, you can say, the most promising extreme points. So these are the ways or possible ways to compute or to calculate the extreme boundary points responsible to represent the target class in better way. And once we're able to identify those promising boundary points, it is done. And if we have boundary, we have mean, it is easy to compute that the incoming points are whether anomaly or belongs to the target class. There are comparison chart is given. Okay, the farthest boundary point estimation is compared with the proposed method of Lee and Zhu. And if you see the accuracy, the LBP is most promising in terms of computation also. Okay. You will see this average training time and sample reduction time and the accuracy also. So this LBP has been proven most promising. Coming to the target class guided feature selection and reduction mechanism. So basically, like conventional binary and multi-class classifiers, data preprocessing is very important step. It includes maybe data cleaning, data balancing, and not necessarily data balancing, not necessarily for one class of classifiers. If the target class is well defined, and the processing technique also includes feature selection and transformation, feature reduction, because all these things are going to affect the performance of these machine learning models very deeply. So, text ETL, ER ETL, UTL, and Frank ETL demonstrate a different variation of feature selection mechanisms as damage reduction approach with principal component analysis, PCA. So it seems very simple, but the thing is that if you deploy or you try to deploy principal component analysis, as it is a nonlinear technique, it's a unsupervised technique. It has variants of linear and nonlinear. So it is not suitable directly for the third class learning. At the same time, if you talk about the variance captured by the components of the principal component analysis, no components basically evaluated by the PCA, and it is of high variance, it doesn't mean that it is going to become a good representative because the high variance is going to split the third class itself. And the problem arises when we have deceptive similar classes, samples of deceptive similar classes in our training sample, if we consider that. So based on this phenomena, all these researchers have identified that it is not always important that the higher eigenvalue principal components are very important. It has been proven that the eigenvectors with small eigenvalues may play a big role in classification if we talk about the class learning. At the same time, uh, GL also prefers the radius recursive feature elimination approach to eliminate the features so that the ant will be able to extract the most promising features as promising features subset. In 2016, Nagabushin ETL had been proposed a three-tier target class supervised feature subsetting technique, where in the first stage, the primary objective was to eliminate the features, and second stage, if surely the redundancy has been eliminated by rejecting redundant features, and the last stage, optimal feature set is derived from the subsequent subset of features. So actually, in case of the static class guided feature selection and reduction, not too much work has been done. Okay, at the same time, Malikisif EL have been shown that the better classification accuracy based on the good feature selection. So here we can say that SFC, LIG, HIC, RFC, so all these are the abbreviations. Like suppose if I talk about LIG, it is uh, uh, low information gain, then random feature selection is RFS, then random feature from feature cluster. So all these are techniques have been proposed. And the objective was to create even class classifiers. So not too much work has been done towards this feature selection, especially guided by the class itself. So a lot of scope is there uh, towards the anomaly detection. If we know that yes, we have a single class samples for training, a class sample for training, then how we should extract the features or select the features, or we should transform the features. So we'll see the possibilities in the section. Okay, so one of the methods have been recently proposed by some GTL, and it was basically looking to guide the model to learn or to learn the feature subset along with the most along with the proposal to solve the most complicated issue, that is, you know, basically hyperparameter tuning of a particular classifier. So method is known as the learning the entire class features feature subset, that is LTCFS. And the idea is very challenging that, or very, let's say, it's small, but it has big impact. Like suppose once you have done the eigenanalysis over the target class samples, the most important thing that we should know, or we should come out with some decision that which principal components or which eigenvectors of covariance matrix of that target class are important. It has been already observed that it is not a good practice to consider always the higher eigenvalued eigenvectors of that covariance matrix. In place, you should think about some novel technique to reject the less informative eigenvectors from the covariance matrix. So to reject the eigenvectors, less informative eigenvectors from the covariance matrix, so straight away we can reject the lower valued eigenvector because they do not contribute generally in the in terms of variance. But if we talk about the higher variance components or higher variance eigenvectors, then surely they will misguide the learning model because the higher variance never ensures that it is going to capture the current class samples only. If we talk about supervised nature, so in that case, the higher eigenvalued components or eigenvalued basically eigenvectors must be rejected also because they may misguide the learning models. So now our technique has been proposed, and based on these eigenvalues, eigenvectors have been rejected, and those eigenvectors are basically computed with the help of feature values and a way of extracting which features are important in particular extraction of each eigenvector. Okay? And based on some statistical analysis, observation has been done, and uh, feature subset have been extracted, and those feature subset, the feature subset is basically uh, giving most promising result compared to the current features subset because the other features were misguiding the learning model in terms of anomaly. Okay. And in the same concept, suppose we want to transform the features from the higher dimension to the lower dimension, the phenomena of extraction of most promising eigenvectors of covariance matrix is very important. So once you know via some rule that yes, these eigenvectors are most promising compared to the others, compared to the higher valued and the lower valued eigenvectors, those eigenvectors may be used to transform the higher dimensional samples to the lower dimension. And it has been observed that results were very promising if we were able to identify those important eigenvectors. So that phenomena is known as learning target class eigen subspace. Okay, coming to this temporal space and the distributed space that we were talking earlier, because the scenario will become more complicated when we'll come to the big data. So can we think of that whether this solution can be explored for the distributed and temporal environment? So right now we're not talking about the temporal level of features. We are talking about temporal level of samples, training samples belonging to the target class. So the first phenomena in case of the temporal space is the sample reduction. So as we have already seen that farthest multi-mode estimation was most promising compared to the other variations of sample reduction technique. So here the idea is very simple that suppose at time t, the first batch of sample is arriving at time t plus delta t1, the second batch of sample is arriving. So for each step, if we basically apply this MBP, the farthest point this boundary point estimation algorithm. At the same time, it's a step we are considering that uh, yes, there are some selected samples, some rejected samples. Okay. The sample, second stage, you're reconsidering all those things, and at the end, we are able to find out that which are the final, which could be become the final training samples. So uh, this work has been explored over the distributed platform using a Spark, and it has proven that RDP, yes, surely is able to keep the most promising result without any iterations. So this is the algorithm that samples are coming from in batches B1, B2, Bn like this. At the same time, uh, the FPP is applied for each step. Same time, at t plus t delta and the samples are this. Uh, we must train this basically one class of the machines using this identified final training set. So results was promising. Coming to this, uh, what about that learning the feature subset guided by the type class? So again, the same principle has been adopted and the same platform have been used over the Spark platform. And there are batches B1, B2, BA, and LTCFS has been applied. And integration, the most common features have been extracted, and at the end, the extracted common features were not surely very less, but approximately 70 to 20, 30% of the original feature space, and they were able to give the optimal performance. This is going to be the algorithm, and yes, you can see that stage 5 we have the 10 plus 1 stage, we have the feature selected by the algorithm, and the one class classifiers were able to give the promising result where the FS and FR the selected rejected features. Coming to the feature reduction, that is feature transformation. So there is a little bit complexity that you may think of, like suppose it's time t, there is one batch is running B1, let us assume. And at B1, the expected number of eigenvectors, most promising vectors, are suppose X. So we cannot ensure that at time t plus delta t1, the eigenvectors extracted from this batch of samples will be exactly X. It may be less than X, it may be less than greater than X. So what could we do at that time? If we are going to reject the extra eigenvector that has been computed from the next batch of the sample, it is going to misguide the system because we are going to basically discard some information from the eigenvectors. So what we must do, we must go for some other options such that if the number of eigenvectors is not similar for different batches of the temporal level of batches, so we must use or we must consider the uh, eigenvectors or the knowledge matrix basically that is supposed to compute in this, you can say, uh, feature transformation process. We must consider the uh, maximum size of the knowledge matrix. Suppose at time t we have the knowledge matrix x, but suppose at time t plus delta t1 we have knowledge matrix of x minus 1. So we must consider the knowledge matrix of size k. But what about the knowledge matrix obtained at stage t plus delta t1? So at that time there are some strategies. So the best strategy that has been identified is that go for the Hadamard quadrant. In that case, in case of the missing eigenvector, we must just replace with one, so that we do not want to lose any information from the earlier recognized information. And at the same time, this Hadamard product is mostly definite, semi-definite, and it follows the associative law, and it also minimizes information loss because it is not basically going to discard the earlier obtained information. So in the last stage, you may have the kn plus 1 because it's done for n plus 1 stage. And using this knowledge matrix or knowledge grid, we may transform our feature to some lower dimension feature. And this is the algorithm. After finding the knowledge matrix, the final knowledge matrix, it's step 4, and step 5, we can transform the whole samples, that have been gathered earlier can be transformed using that knowledge matrix K, and the transformed information can be used to train that one classical classifiers. And the result was promising without. At the same time, we talk about the temporal arrival data, that means time series data. So as we have seen that most of the work so far were dedicated towards the multivariate time series analysis. But this was the work that has been proposed toward the univariate time series, where a single variable is supposed to observe, n number of times. So the complexity arises when you have huge sample space and how you're going to basically represent the time series data and how are going to choose the number of best promising samples and how are going to choose the best promising observation points. Those observation points must be considered as features. So in this part of work, what has been done, the DBR techniques or dissimilarity-based techniques have been used so to basically learn that how to represent time series data. So time series representation for efficient computation is a challenging task always. The DBR method will represent an unknown instance via direct pairwise comparison, a set of reference instances, and a proven effective for multi-class classification so far. But this work has been done to show that yes, DBR techniques are useful also toward the target class learning. Okay. So a lot of DBR techniques are here in terms of literature, but in this basically you can say this part of work, 16 DBR techniques have been used to represent the time series or univariate time series in best way. And apart from that, the predefined prototype techniques, a lot of prototype techniques to select the most promising samples from the given sample space in terms of multi-class classification have been proposed. But it has been shown in this work that those prototype methods can be used in target class learning. And it is assumed that only the target class learning, target class samples are available during the training. So here we have used 11 uh, prototype selection methods that have been already basically you can say discussed about the multi-class classification, but it has been answered that these approaches are useful for third class learning also. And it has been assumed that only the third class samples are available in memory. And at the same time, the objective of this work was to just show that yes, we can do the concurrent sample reduction and the feature reduction on a given set of time series data to learn the temporal nature of the data. Same time, if DBR technique is allowed as a deployed, we can transform the data in some vector representation, and using we must choose the target class first, assuming that only the class samples are the rest of the samples or classes of other samples treated as, you can say, these are basically anomaly. At the same time, the computation of eigen knowledge matrix is needed so that we can learn the features. The features here mean that we are looking to observe the most promising occurrences of that instance of those instances. Based on that, we must observe, we must extract the most promising observation points. So that is considered as, let's say, that feature selection. So in this way, this particular work can be divided in three parts. The first one is data representation or vector representation of the univariate time series. The second one is the selection of the most promising, say, prototypes guided by the third class itself. The third one is the most selection of most promising observation points or the sample stamps to basically, decide that which basically observation points are contributing too much information. And finally, after extraction of all those things, the one class classification models were get trained and the results was promising. Okay, and for experiments, the one class of vector machine and one nearest neighbor basically were experimented, and it has been observed that yes, the performance was compar comparable with other existing models. And surely, this work can be divided into four parts. Data representation using DPR, sample length reduction using knowledge grid, and training sample reduction using prototype, and surely the last one is the one class classification. And it has been observed that almost 16% eigenvectors were basically able to identify, able to perform, good. And the data set was basically a collection of 85 univariate data set and also known as UCR UA archive. Okay. It is also known as data set generated by University of California, okay, University of East Engineering. So, and it has been also shown that one class of vector machines were better compared to the one nearest neighbor. At the same time, it has been also observed that one of us laser, that is DPR, and using the Bayesian Gaussian mixture together exhibit better class representation. Okay, the most important thing is that when the incremental farthest boundary point estimation and the incremental LTC is applied to the same problem, so the process was able to achieve 13% of the eigenvectors as promising eigenvectors. Okay. At the same time, the batch size was fixed to 5 to 10 and 20% of samples. And at the same time, the training samples obtained by the IBPE was approximately 70%. At the same time, there is one phenomena that is pinball on class one support vector machine has been also tested, and it showed better result compared to the conventional one class support vector machine and SVDD. Okay. So this reason behind this pinball one class support vector machine and its behavior we'll discuss in after a few slides. Coming to the again direct class learning in the same data set of UCR and UA. Okay, again the same dissimilar to DBR and prototype methods have been applied, but this time, apart from selecting the eigenvectors, the focus was to select the features. And again, the results were promising, and approximately 30% features were sufficient to give the proper performance. But we'll compare that what is the difference between feature transformation and feature selection, and surely the feature transformation gives better performance because it is able to give less number of features for most promising research. So surely the LTCE is better than LTCFS. And remember one thing, all these things are guided by the target class only. So surely it is going to be playing a big role in multivariate time series analysis also. And once the incremental version of this sample selection or the feature selection have been applied, again, there was a big impact of these variations over the Spark platform. So it has been observed that only 23% features were able to represent the target class. At the same time, 20% samples were able to represent the target class average because there were 85 data sets. No? And in case of normal one, there was 30% features were extracted as feature subset. Yeah, the same theory has been extended to distributed environment, where it has been assumed that the samples were distributed across the slaves, and for each slave, the algorithms are being applied, like MBP, to each slave. And after getting the, basically, can say, after getting the most promising samples from each slave, all the selected samples were arrived to the master node, and finally the MBP is being applied, and the results were promising. So this was the algorithm. So blocks, it basically can be divided randomly. It can be considered that it is divided basically homogeneously. Like suppose there are m number of nodes, so the total number of sample is x. So each, you can say, slave must have x divided by m samples. But the algorithm MBP is same. Likewise, the feature selection method is also plays a big role in distributed environment. And coming to this again, this feature transformation technique, again, the size of knowledge matrix that has been opted from different batches belong to different slaves are going to play a big role. Okay. In that case, again, surely the knowledge grids obtained by different batches will be of different sizes. But how to cope up with this situation? We cannot neglect the eigenvectors of an identified eigen knowledge matrix. So for that, again, the Hadamard product has been used and result were promising. So coming to this anomaly detection using, also it was all about the feature learning and the sample learning guided by the target class. But again, let us see that how this anomaly detection is basically, can say, can be achieved using one class supported classifiers. So one class classification is useful when majority of data belongs to single class. One of the classes is significantly undersampled. It means that you may have, again, this is the same thing that, yes, one of the sample is known as target class and the other samples are as anomalous. Here, the one class separated classifier algorithms surely builds, the flexible boundary around the target class data so that at some type of observation we can conclude that yes, the testing sample that is incoming, okay, whether it belongs to target class and whether it does not belong to, I can say, target class, or it is an outlier. So these data boundaries characterized by observation that are designated as support vectors. So surely these boundary points deciding on the boundary of the target class are known as support vectors. And the advantage, yes, we will not assume any distribution except the Gaussian one. If it is not, we have some solutions to change the distribution to Gaussian in nature, and we can work upon. So best example that we have not seen so far, that in case of machine monitoring, data on the working condition of a machine are in basically huge in nature, whereas the information about outlier system failure are few. So how to cope up the situation? So this is best application everywhere in every application domain in case of medical diagnosis also, because the samples of bad cases and good cases are so much in balance that we must always focus on either of these sides. At the same time, suppose we talk about a toy company or toy manufacturing company, the manufacturing of good samples are huge and manufacturing of wet samples are less. So likewise, it is applicable to everywhere. So that is why this one class classification algorithm, especially one class classifiers, are going to play a big role in anomaly detection. The same thing, this is the SVDT and the one class of vector machine. No doubt the objective functions are different. The boundary structure is different. In case of SVDT, we have spherical boundary. In case of one class SVM, we have one hyperplane. But if you talk about the unit norm space, so we can basically map one class of vector machine to SVDT. And we can conclude that both SVDD and one class of vector machine plays same in unit norm space. So either of the algorithm we can choose, and we must think about the third class guided dimensional reduction, third class guided sample reduction, and no doubt classification, one class classification. Coming to this one application of this one a variant of one class of a vector machine. So the variant is known as the pinball one class of a vector machine, and here the loss function that has been incorporated earlier with one class of a vector machine is inch loss, and you can see the difference based on the value of tau. This can be made more flexible. And no doubt this pinball is not going to add a computation overhead and converges to conventional one class of vector classifier when pinball last parameter tends to 1, that is tau is equal to 1. Okay. So let us see that how this classification algorithm basically is able to fight the deep learning models. So this is some mathematical expression that is not necessarily taught in this place to discuss. But the objective function, once we see this, in place of this penalty, we have incorporated the pinball loss function, and we can see this dual problem of, and at the same time, it is also satisfying liquidity condition. At the same time, at the end, we can see that, yes, what should be the output in this equation 8. So coming to this application that the objective was proposed a bit earlier, and it was about how to diagnose COVID-19. At the time, the number of XR images were very less. So it was not possible to train the deep learning models very efficiently at that time. So what people did, they just upsampled the COVID-19 sample from the given data set, and they have just tried to balance the data set and try to build the multi-class classifier or binary class classifier. But the phenomena that suppose we have only COVID-19 samples, and we want to diagnose that whether the person belongs to COVID-19 or not, it is going to be a tedious task. So this problem was resolved by this one class classification model. So in that, what have been done? So the no doubt the preprocessing was needed. So preprocessing was done in pixel level or brightness level, or in terms of image clarification or cleaning. Once obtaining the images of all these data sets, the data sets of COVID-19, RSNA, and then all these data sets have different behavior. This COVID-19 is having two classes, it is having two different classes, it's having two different classes. Once we'll see the distribution the sample of COVID-19 was very less. So how to cope up with the situation? So the objectives are show or demonstrate the applicability of this one class classification to detect the anomaly. Okay? Because let us assume that COVID-19 is the target class and the other sample is coming from different class. Then if a person is not infected by COVID-19, then surely he must be an outlier or he must be a normal person. So the schematics shows that after pre-processing, the COVID-19 CXL images were trained using pinball 1 class SVM, and the rest of the samples were treated as the test samples. And the objective is to show the efficiency. So coming to the pre-processing steps, the adaptive total variation method and automatical equalization have been used. You can see this diagram that this was the input that we filter mask, and these are the outcome of these two different basically pre-processing techniques, that is refined or precise image and noised images. Okay. And these were the results. So basically since we compared with deep learning models, it has been observed that the pinball loss function were most promising. Sometimes the conventional one class of machine was giving equal performance, but they're far away from the deep learning models. Apart from the phenomenon that deep learning models need huge computation power. Their data crunchy, they need more data, so sampling was needed. So a lot of pre-processing also needed. So things were there. So if you go for that one class support vector machine, one class support vector classifier, so surely with less computation time, less power, less efforts, be able to give somehow equal performance. And it is not always necessary to concentrate on accuracy. Sometimes it's all about the requirement of power consumption also. At that time, this support classifiers are going to play a big role. So this is one of the comparison in presence of noise. So what has been done once the purification has been done in images, the Gaussian, Laplacian, and uniform noise has been introduced. And at that time, it has been observed that yes, the deep learning models not at all the pre-existing deep learning models I'm talking about. So we're not able to cope up the situation. But no doubt this pinball one class transformation played a big role. And we can see this bold results. So it's most promising. Apart from there, some UCI data set were also experimented with one class and pinball one class productive machine. So most of the time, this pinball was strictly, can say, even good results compared to the conventional one class of productive machine. So coming to this was all about the earlier section was all about this use case of that one class classifier for say for anomaly detection. So here, let us see that, and all those things were done in supervised mode. So suppose we want to learn the target class in unsupervised domain, then what should be the approach? There is one work that has been done based on the CORD19 dataset. It was a scholarly dataset, and a lot of after pre-processing, the observation has been done, and one pipeline of clustering algorithms and parallel one class automation has been proposed in this work. And uh, it is basically offering a bottom-up approach to mine the COVID-19 scholarly article. So COVID-19 articles are basically belong to different classes. It may belong to humanities, it may belong to uh, management, it may belong to economics, it may belong to, let's say, medical domain, it may belong to computational domain. Then how a person will become to know that each articles of his or her interest. So the objective was that. So it offers the bottom-up approach to mine this COVID-19 scholarly article, and the dataset will use the CORD19 dataset. So because initially the clustering techniques were used to create the different clusters. So the sample is available. So some pre-processing were done. to represent those text into vectors, and the clustering were done based on the clustering techniques, pre-existing techniques, and then the task assignment was done, and parallelly, one class of vector machines would get trained on different clusters. At the same time, the new incoming sample were tested whether they belong to this category or not. So this is the whole schematic of this. So initially the articles were coming. So this is embedded vector space has been done. Then the clustering has been done. Then no doubt using original feature space, the OCSVMs has been trained, or even after DR, dimension reduction, the OCS has been trained, and then final testing has been done. And the results were promising, just giving good, basically, you can say, outstanding results. So thank you very much for this part 3.